On your first day, so imagine you just got hired. You've been tasked with setting the production levels for a new product line called XAMPS. You see that the cost of producing Z XAMPS is 25 plus Z. So we have the cost, and that the market forecast report predicts that the revenue for Z XAMPS is 21 arctangent of Z plus 4 log 1 plus Z squared. I like these people. How many XAMPS should be made to maximize profit? All right, that's why we're here, making money. All right, so our options are 8, 10, 12, 14, or 16. The answer is?
10.
Wow, that was quick. You are correct. The answer is 10. Nice. All right, so how do you do this? You channel your inner econ 1010 and say, how do I find profit? Well, it's how much money I make, revenue, minus how much money it costs me, cost. So we take the revenue, subtract the cost. That's a function of one thing, Z. And it's okay to be Z. I don't know why I put an X here. This is d dz. So take the derivative with respect to Z. And you get 21 over 1 plus Z squared plus 4 times 2Z over 1 plus Z squared and minus 1. And we set our derivative equal to 0. We can move the 1 across. Put these two, since they have a common denominator, over the same denominator. Cross multiply. And we get down to a quadratic, which is factorable. What are the odds? Really good. Because we like our students. We want them to have nice numbers. And so you end up with two possibilities. Either make 10 XAMPS or make negative 2 XAMPS. Well, you can't make negative 2 XAMPS unless you count making negative 2 as going to your competitors and breaking some of theirs. So we can rule that out. So that just leaves us with one possibility. And so we should set our production level at 10. All right, so there we go. And this was an optimization problem. How can you tell it's an optimization problem? What are some clues?
Maximize profit.
Yeah, you want maximize. Whenever you see words like maximize or minimize or things which end in est, you want the bestest profit, the mostest profit, right? So anytime you see that kind of setting, you're thinking optimization. All right, so our thought for the day comes from Stuart Smalley. If you're not familiar with Stuart's work, you can look him up. There's a fun clip of him with Michael Jordan. This was actually a character on Saturday Night Live. And he said, I'm good enough, I'm smart enough, and doggone it, people like me. It's one of those self-affirmations. And I think, they get a little bit of a negative rap these days. But I think it's important to have a positive self-image. How you think about your ability to do math affects your ability to do math. If you think you're going to be bad at math and that you're going to do bad at the exam, you will find a way to make that happen. If you think that you are somebody who can be good at math, can learn, and can improve, and maybe even do okay or good on the exam, you can make that happen. So you have to have a positive self-image. You need to be your best cheerleader. Because, you won't always have people around you who will lift you up. I hope you do. So make sure you're lifting yourself up. Don't put yourself down. All right. So that's our thought going into exam week. Have a good, positive mental attitude. All right, deja vu. This is basically the same thing as before because I just copied it from the slides from last time. We're talking optimization. Our goal, we're trying to set things to make things as big or as small as possible. ultimately optimization comes to balancing trade-offs. We're trying to have multiple things come into play. What's the right thing where we get the most out of our situation? How do we do it? Make sure we understand the problem. In other words, what are we trying to optimize? What in your situation can vary? If you have multiple things that can vary, and that can sometimes happen, what are the relationships between those things? Because ultimately, looking ahead, you need to get down to a function of one variable. We are single variable calculus. Don't worry, multivariable calculus is coming. And it's going to be a great time in a year from now when you have that class. But okay, if you can, draw a picture. Because I think pictures can help get some intuition about what's going on. Once you've gotten your function, classify critical points. In other words, take a derivative. That's your tool. Your tool is the derivative. In some sense, this exam is, can you use the derivative, which we learned about on the first exam? So we're getting into applications. And finally, make sure you give your answer in the appropriate form. They might be asking you for the absolute max. They might be saying, where does it happen? They might be giving you a geometrical shape. They may say, okay, what's the volume? Or they might say, what are the dimensions of your shape? So make sure you understand what they want as the answer. And give them the answer that they ask for. And be prepared. You might have to justify being a max or min. All right, so that's the quick summary. And now I just have a whole bunch of problems. So let's see. I can tell you the selections, and then you can pick, or I can just pick randomly. I have putting a TV on your wall, Mario problem, classic. 2D Mario, yeah. You got folding some paper, building a container, and one about tangent lines. Any preferences to start our day with? The Mario problem. Now, I cannot give you the full story of the Mario problem on paper, but let's see, was it today or was it last time? Oh, unfortunately, it was the last time. So if you have the handout from last time and you look on the back, you'll see why. It would take me a whole page. So I'm just going to give the Cliff Notes version of the Mario problem. So there's a picture here, and you are trying to connect Peach's castle to Yoshi's island, and you're going to have pipes, because Mario, after all, he's a plumber. And so there's these yellow pipes. Now there's two types of pipes. There's pipes that run along the shoreline. There's pipes that go in the water. And because on the shore, you don't have to worry as much about the water, they're a little cheaper. So the pipes along the shore cost 100 gold coins for a kilometer. Now you might think 100 gold coins, that's like a life worth of coins, but that's not so bad, right? Pipes in the water cost W gold coins for a kilometer. And you might say, wait, what? What's W? That's the problem. We're told that the cheapest setup, in other words, the fewest gold coins, is to do the following: to have the pipe go halfway along the shoreline and then go the rest of the way along the water. The goal is, how expensive does that pipe in the water cost? So it's related to an optimization problem, but now we tell you the answer to the optimization problem. You've got to figure out the problem. Isn't that fun? I think so. All right. So let's think about what's happening here. So when we talk about optimization, what are we optimizing here? Like, is there an S word that jumps out? Cheapest. Okay, so when we're thinking about setting up the optimization problem, we're setting it up in terms of cost. So we say, okay, so we have a cost thing. So let's figure out our cost. Now there are two types, there are two types of pipe. So let's split it into two sections. And I've marked this as X, so we'll just have X be the amount of pipe along the shore. How much does this cost? Well, if you're along the shore, how many gold pieces per kilometer? 100. How many kilometers do we have? Well, in generic, how many do we have? X. Okay, so our cost is 100x. This is the shore line. Then we have W times this length. Okay, so how do we figure that length out? Oh, yes. Pythagorean theorem. We have this length is 6. Do we know any other length?
2.5. Yeah.
Well, again, you're thinking of 2.5 as being the answer. Think generically as a function of x. So what's that length?
X.
Well, x is 5 minus x. So what is the length in the water? Pythagorean theorem says it's the square root of 6 squared, 36, plus 5 minus x squared. Yes? Okay, now 6 squared, as somebody mentioned, is 36. 5 squared, we might as well throw that in there too. So this is 36 plus 25 minus 10x plus x squared. So 36 plus 25 makes 61. That sounds like an interesting number. 61 minus 10x plus x squared. Okay, so there's the cost function, where w is some number that we don't know. And the second part here, this is in the water. Okay, so what can we do? And why do we do that? Yes, we have our tool. We have our cost as one variable, x. After we do that, we take a derivative because it's our only tool, right? No. We take it not just because it's our only tool. We're looking for critical points. So we can take our derivative. Now, thinking ahead, if we're going to take a derivative, let's rewrite this in a calculus-friendly way. So 61 minus 10x plus x squared to the 1/2 power. That's calculus-friendly. So we have c prime of x is equal to 100. Okay, that's good. W, and then this expression. Well, 1/2. 61 minus 10x plus x squared to the minus 1/2. Anything else? Times negative 10 plus 2x. Okay, well, that's 100 plus, here I can take this 2 and divide it upstairs into that minus 10 plus 2x. So I can write that as w times x minus 5 over this square root. So this is the square root of 61 minus 10x plus x squared. All right, so that's our derivative. What's true? What do we know? And on a side note, this is from an exam, except that the exam had the story filled up like half the page. It was a great story. You had Luigi came, and you had to pull out your receipts because of Mario's project, and you'd lost. It was a wonderful story. All right. So what's true?
One of the critical points has to be 5 over 2.
We know that the critical point is 5 over 2. Why do we know that? Because it tells us. It says, hey, the cheapest one is at 5 over 2. The cheapest thing has to occur at a critical point. So, what does that tell us about 5 over 2 in this function?
It has to equal 0.
So if you plug 5 over 2 into this function, you get 0. So 0 is equal to c prime of 5 halves. So we plug it in. That's 100 plus 5 halves minus 5. Well, that's actually not too bad. That's a w times minus 5 halves. Now, the downstairs, we probably need to do some work. We'll do some work on the side over here. So we're going to take 61 minus 10 times 5 over 2 plus 5 over 2 squared. All right. Well, 61 subtract 10 over 2 is 5. So this is subtract 25. And then 5 halves squared is 25 over 4. Yes? 61 subtract 25?
46.
Sorry, 36. So this is 36 plus 25 over 4. Does that look familiar yet? Don't worry, common denominator. 36 is also something over 4.
Cubed.
36 is
No.
144 over 4.
Yeah.
144 over 4 plus 25 over 4 is 169 over 4. So that's what's underneath the square root. Now, what is the square root of 169 over 4? 13 over 2. Wow. It's like we planned it to have nice numbers. And you're probably thinking, that's not nice. But relatively speaking, it could be worse. Okay. Well, what do we do? Solve for W. We can cancel the over 2's. And then we have enough space here. If we move the W term to the other side, we get 5 over 13 times W is equal to 100. So W is 13 times 100 over 5, which gives us so we can do 100 into 5. So 100 divided by 5 is 20 times 13, 260. So the W, the cost for the water, is 260 gold coins per kilometer. And there we go. So that's the answer, 260. Aha! Just as you thought. All right. Nice warm-up problem, right? Okay. Any questions? There's lots of variations of this problem. Sometimes they'll talk about a lifeguard is running out to save a person, and they'll say, they're faster on the land than they are in the water. How far should they run on the beach before they jump into the water to start swimming? There was a dog who was known as Elvis. Elvis the dog, no relationship to the singer. And it was a corgi. And the owner's dog said, Elvis can do calculus. And he demonstrated this by throwing the ball into the water. And what would Elvis do? He wouldn't go straight after the ball. Elvis ran along the shoreline before jumping into the water. And so it was like, okay, Elvis was doing differential calculus. So just think, if Elvis the dog can solve these problems, you can solve these problems. All right. Unfortunately, Elvis is no longer with us. But I actually met Elvis because his owner was from Iowa State. I think graduated from Iowa State. Oh, I guess we should ask, which problem do you want to do next? So we still have TV, Mario Part 2, a paper strip, storage container, tangent line.
Part 2.
All right, Mario Part 2. Okay. So this one is a 2D Mario problem. So help 2D Super Mario build the boat. So the boat has dimensions shown below. So you have essentially two things to toggle. You have A and you have B. And the boat is rectangular in the back, but the front is a quarter circle. So Mario has some material. 4 plus pi length worth of material. So that says if you do the part here, that totaled up needs to be 4 plus pi. Now the question is, how should you choose A and B to maximize the area in the boat? And that's the shaded area. Let's talk about things that have to be true. What is it we're trying to optimize? What is it trying to maximize? How do we know we're trying to maximize the area? That's a pretty good clue. It tells us. It's almost like it wants us to know things. What's the area? Well, there's two pieces. What's this area? A times B. What's this area? 1/4 pi a squared. All right, so you have area, AB plus pi fourths a squared. Now that gives us two variables, A and B. That's too many. We want one. So what's the relationship? Well, what else do we know? There's a number here. 4 plus pi, what should that be equal to? A plus B plus 1/4 the circumference, because we're just using the outer port, 1/4 of 2 pi r, which becomes pi over 2a. All right, so the answers are 2 and 2. Area, we talked about. Length, a plus b plus pi over 2a is 4 plus pi, which gives us a relationship between a and b, which is kind of messy, but math can be that sometimes. So you can solve for b in terms of a, substitute what b is, and you get a single variable. Take a derivative, set it to 0. Your stuff with pi's cancel, you end up with a equals 2. Plug a equals 2 back into b, and you get b equals 2. So a equals b equals 2. That's the ideal boat. All right. Well, good thing that's not the one on the test. Okay, we still have a few more problems. So, TV, strip of paper. TV, all right. You have attached a 5-foot tall TV to your wall with the bottom of the TV 9 feet above the floor, because as we often know, most dorm rooms are indeed over 14 feet tall. When sitting on your couch, let's draw some pictures here. So we have a tall TV. Is that realistic to have a 5-foot tall TV? In a math problem, yes. In reality, no, it's too small. But then there's 9 feet here. When sitting on your couch, okay, so here we are sitting. We should draw the couch too, because otherwise, it won't be realistic. All right, so here we are. Here's our couch. All right, it's a leather sofa. We can afford it because we have that big wall. Okay, so as we're sitting, our eye level are 4 feet above the floor. So this is 4 feet up. Now, the question is, how far back should you be, so we'll call that x, from the wall to maximize the angle that you see. So in other words, what this picture is, you want to get the best view possible. So you want to have that TV take up as much of your sight as you can. So we want to make theta large by choosing x appropriately. That's the problem. All right, fun problem. What do we do?
Well, you can change the total height from 14 to 10.
All right, so we can set that to 5. And notice this is conveniently a right angle. And when we see a right angle, we prefer triangles with right angles. We just feel that there's something right about them. All right, so let's think of the angle here as actually being sort of a difference of two angles. There was a hint that says think of it as a difference of two angles. You have a big angle and a small angle. We'll call the big angle alpha, the small angle beta. Do we know anything about this angle alpha? Can we express it in terms of x? So we have an angle. We have the adjacent side. Do we know the hypotenuse or the opposite side? We know the opposite. What relates adjacent to opposite? Yeah. Channel your inner SOHCAHTOA, right? You may see a triangle. Know what trig functions go with which relationships. We see an opposite, we see an adjacent. That puts us firmly in the TOA section here. All right, so we're in TOA. So we're going to be doing tangent. All right, so we can say tangent of alpha is opposite over adjacent. What about tangent of beta? So tangent of alpha is 10 over x. What's tangent of beta? 5 over x. Now, what do we want? We're trying to optimize theta. Theta is alpha minus beta. What is alpha? We said what tangent of alpha was, but what is alpha? It's arctangent. And now you're like, I know why Steve asked this question. Maybe you don't know. It turns out I like arctangent problems. And so if you keep going, Calc 1, Calc 2, Calc 3, you're going to be like, Steve, you should talk to somebody. Nobody should like arctangent this much. But, all right. Anyways, minus arctangent 5 over x. Okay. Have we had a great breakthrough on this problem? Or has this just made things worse? So, what is it we're trying to optimize? Theta. And we're trying to choose the right value of x. Do we have theta as a function of only x? Yes! We are in our happy place. Other than what needs to happen next? We've got to take some derivatives. Okay, so we're taking the derivative of theta, theta prime. So, derivative of arctangent. 1 over 1 plus 10 over x squared, right? Derivative of arctangent, 1 over 1 plus the inside squared. Anything else? Okay, negative 10 over x squared coming from chain rule. Because you have to take the derivative of the inside. So this is like 10x to minus 1. So this is equivalent to minus 10 over x squared when you take the derivative there. Okay, so that's the first term. What about the second term? Well, deja vu. 1 over 1 plus 5 over x squared times negative 5 over x squared. Yes?
Where'd you get the x squared from?
So think of 10 over x as 10x to the minus 1. So when you take the derivative of that expression, the 10 stays, and the derivative of x to the minus 1, the minus 1 comes down, x, and you subtract 1. So minus 1 makes minus 2. So that's an x squared downstairs. All right. So, what do we do with this? Set equal to 0. And now we have to solve for x. Now this looks bad, but maybe it's not as bad as you think. So let's clean this up. So upstairs in the first term you have negative 10. Downstairs I can imagine multiplying the x squared through, so that's x squared. And notice this is 100 over x squared times x squared, so it's x squared plus 100. On the second term, minus minus makes a plus 5. Again, I'll multiply the x squared through, so 1 times x squared is x squared. 5 over x squared is 25 over x squared times x squared makes plus 25. And we set that to 0. Okay. Well, it's times like this I wish I wrote smaller. But we can move a term across. We get 5 over x squared plus 25 equals 10 over x squared plus 100. And what can you do here? Cross multiply. Get rid of your fractions. No more fractions. Woohoo! Okay, so we'll try to sneak our answer up here. So 5x squared plus 500, so I'm multiplying across, equals 10x squared plus 250. Well, move things around. You get 250 is equal to 5x squared. So that says x squared equals 50. So what is x? Square root of 50. Why is it not negative square root of 50? Well, you can't go into the wall. So it's positive square root of 50. So x equals square root of 50 feet. Okay? We fit it in. And we even have time to draw a little space to draw smiley faces. Like how happy we are to do a problem with arctangent. All right. Any questions? Okay. So let's do the paper one, the strip of paper. A long strip of paper has a width 9 centimeters. At a point P, so there's a point P, you're folding the top corner so it touches the bottom side. Where should P be along the edge to maximize the area of the shaded triangle? So there's this little triangle that's being formed. You want to get as much area as possible. What should P be? So let's blow this triangle up. And let's call the length up to point P, let's just call this length x. And on a side note, it is a right triangle. Do we know one of the other two sides? And why do we know it?
The hypotenuse would be 9 minus x, wouldn't it?
The hypotenuse, if you think about where this comes from, this part is coming from the part that got folded over. So this is 9 minus x. All right, good. So we know two sides of a right triangle. So if you know two sides, what does that tell you? We can find the third side. Pythagorean theorem. So this would be the square root of, we're going to take the hypotenuse squared, subtract the other side squared. And if you multiply this out, this would become 81 minus 18x, and then plus x squared minus x squared. So it becomes 81 minus 18x. If you like, you can also factor a 9 out of both terms. So this is the same thing as 9 times 9 minus 2x. So you can write this as 3 times square root 9 minus 2x. Okay, so how do you find the area? Area is 1/2 base height. And now our height is x, and our base, we know what it is as a function of x. So area is 1/2 times x times 3, and I'll write this as 9 minus 2x to the 1/2 power. Three halves x, 9 minus 2x to the 1/2. All right, so our area is down to a function of a single variable. That's the hard part. Well, that's a hard part. What comes next?
Derivative.
Yes! Aha! You've cracked the code. Get it down to a function of one variable and take a derivative. It's a very short code. So that makes it easy to remember. All right, so what rule do you need to take this derivative? Chain rule and product rule. So the derivative of the first, that would be a 1. Leave the second alone. Plus the first, which is x, times the derivative of the second. Okay, chain rule. The 1/2 comes down. 9 minus 2x to the minus half power. And what else? Times -2. Now the good news is that the 2's cancel. Let's factor out the 3 halves. Both of these have 9 minus 2x. Let's factor out 9 minus 2x. But which power of 9 minus 2x are we going to factor out? The smaller one, which is the -1/2. Okay, from the first term, what's left? We got the 3 halves. 1 don't need to worry about. We had 9 minus 2x to the 1/2. We pulled out 9 minus 2x to the minus 1/2. We are left with 9 minus 2x to the 1. 1/2 subtract minus 1/2. From the second term, we got the 3 halves. We didn't get the minus. We didn't get the x. And I think we got everything else, because we pulled out the 9 minus 2x to minus 1/2. 9 minus 2x minus x, also known as 9 minus 3x. Okay, where are the critical points? Three, and there is a place where we're undefined, which would be at 4 halves. If we put p at 4 halves and we fold, what's happening to our paper? It's going to fold exactly in half. So it folds right in half. There's no area. So that tells us the only critical point that has any hope is x equals 3. And so that's got to be the answer. So where should P be to maximize the area of the triangle? It should be 3 centimeters from the bottom. That's where we should fold. All right. And we're out of time. So all those problems we could have done.